Hi, welcome to Basics of Special Relativity, Lecture 2, Axioms of Special Relativity. In this lecture, we're going to lay out the axioms of special relativity, from which we'll derive all of our subsequent results. But first, we'll define some terms that we'll be using in this and subsequent lectures. Okay, let's go. Let's say we have an observer who wants to make measurements of when and where events occur. They define a coordinate system with spatial coordinates x, y, z, and time coordinate t, taken from a clock at rest in x, y, and z. So the observer can describe events like a light bulb turned on at x equals 3 meters, y equals 2 meters, z equals 0, at time equals 3 seconds. These coordinates, with time given by a clock at rest in x, y, and z, define a reference frame. Let's say that the observer is at rest in this frame. That makes it the observer's rest frame. Also, take a reference frame where objects that are not acted upon by forces do not accelerate. Objects at rest stay at rest. Objects in motion remain in motion with constant velocity. Such a frame is called an inertial reference frame. Unless otherwise stated, in these lectures we'll only use inertial frames. We will often, for simplicity, just refer to them as frames. With those definitions out of the way, we are now ready to state the two basic axioms of special relativity. First, the laws of physics are the same in all inertial reference frames. And second, one of the laws of physics is that the speed of light in a vacuum always has the same value, c. We'll now take a look at each of these axioms. Okay, first, what are some examples of inertial frames? Take a spaceship out in space with engines off. Objects at rest on the ship, even if not secured, will stay at rest in the rest frame of the ship. Objects moving on the ship, if not interfered with, will continue moving at the same velocity. The rest frame of this ship is an inertial frame. The passengers can define 3 spatial coordinates of the ship rest frame and use the ship time to describe when and where events occur. Another example of an inertial frame is a frame that is in free fall. For example, satellites orbiting the Earth, like the International Space Station, are in free fall around the Earth. The satellite and all of the objects on the satellite, including the ship's clocks, fall together. This is why objects and people on the space station float. No force pulls them toward any particular part of the station. So, free-falling frames are also inertial. And what's an example of a non-inertial frame? Let's take the spaceship from earlier. What happens if it fires its engines? In the frame of the ship, unsecured objects will accelerate toward the back of the ship. So this is not an inertial frame. What about the surface of the Earth? if you hold a ball and let go of it, it accelerates toward the ground. Similarly, if you throw the ball, giving it some velocity, it will not maintain that velocity, but instead accelerate toward the ground. So the surface of the Earth is not an inertial frame due to the presence of gravity. However, the effects of gravity at the surface of the Earth are actually pretty weak when it comes to relativistic effects. So as far as special relativity goes, the surface of the Earth isn't such a bad approximation of an inertial frame. Okay, with that, let's construct some inertial frames and see what it means for the laws of physics to be the same in any inertial frame. Let's say we have an inertial frame. Now we define another frame, which is identical to the first frame, except that it is offset by constant amounts delta x, delta y, delta z, and delta t. It has coordinates x prime, y prime, z prime, and t prime. So x prime equals x plus delta x, etc. This is also an inertial frame. We will require that the laws of physics be the same in these two frames. We describe this requirement by saying that the laws of physics are translation invariant. This means that the laws of physics don't depend on your location in space-time. We can also take that initial inertial frame and rotate it. Here, we rotate it about the z-axis. This new frame is also an inertial frame, and we will insist that the laws of physics are invariant under rotations of the coordinate axes. This is called rotational invariance. The laws of physics do not depend on direction in space. And there's one more thing we can do. Again, we start with an inertial frame. We define a new frame, just like our starting frame, but we have it, including its clock, moving at a constant velocity, here in the positive x direction, relative to our old frame. We will also require invariance under this transformation. This requirement is called boost invariance. The laws of physics don't depend on how fast your inertial frame is going relative to some other inertial frame. And lastly, we can combine these transformations into more complicated ones. Below, we've done a translation, rotation, and boost. We'll also require invariance of the physical laws under these compound transformations. Okay, we have said above that the laws of physics don't depend on where an inertial frame's origin is, how it's oriented, or what speed it's going relative to another frame. One of those laws of physics is that the speed of light in a vacuum is a constant, c. This means that the speed of light will be the same for all observers in inertial frames. In particular, two observers who are moving relative to each other will both agree that the speed of light is c. This goes against our intuition because other speeds do change from frame to frame. For example, let's say you're riding in a car. This is not an inertial frame due to gravity and bumps in the road, but we'll ignore this here. In the car's frame, you and objects in the car are approximately still, with velocities close to zero. But if that car is moving at 50 kilometers per hour along a road, an observer on the sidewalk would say that you and the other items in the car are going about 50 kilometers per hour. So observers in different frames will report objects as having different velocities. Now, while you're in that car, you shine a flashlight toward the front of the vehicle. In your frame, that light is traveling at speed c. Because the speed of light is the same in all frames, an observer on the sidewalk will also report that the light is traveling with speed c. In particular, the observer on the sidewalk does not report that the light travels at c plus 50 kilometers per hour. So this idea that c is the same in all frames is very weird. Nonetheless, it is confirmed to high precision by a wide array of experiments, so we're stuck with it. As speed is a rate of change of position with respect to time, this is a hint that the notions of absolute space and time that we are familiar with in Newtonian mechanics and in everyday life will have to change. The invariance of the speed of light c from frame to frame doesn't seem to jive with everyday experience. Why is this? The effects of special relativity compared to Newtonian mechanics are small when all the speeds involved in a physical situation are small. The effects become bigger as speeds of objects get close to the speed of light. Because the speed of light is very large, about 3 times 10 to the 8 meters per second, the effects of special relativity are usually too small for us to see in everyday life. Okay, so let's briefly summarize. In this lecture, we've given the definitions and axioms which will be used to derive the effects of special relativity. In the next lecture, we'll give an overview of some of the non-intuitive effects of these axioms. We'll get into the details in subsequent lectures.